Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Now we've gotten to the point where we could actually put a lot of things together, from the spectral type to color diagrams, to distances, to luminosities, to temperatures, to everything, and masses, to create one of the most important tools for all of astrophysics that tells us enormous amounts of information about the types of stars, their futures, their histories, their destinies and their origins. And it's called the HR diagram, or the Hertzsprung-Russell diagram. So let's see what that is. It's one of the most important tools of all of astronomy. Let's check it out. All right, let's go back and get our basics together. All stars are very well approximated by having their spectrum be what's called a blackbody spectrum. And a blackbody spectrum assumes that the object is hot and dense, and that the light can go inside in it and bounce around until it's completely, what we say, thermalized, so that all of the material inside of the star is roughly the same temperature. And as it emits from the surface, well, it's kind of dicey for the star, but right at the surface it becomes the same temperature. And as this light emits from the star, the surface is roughly the same temperature across the entire thing, and can be described by what's called a blackbody. And a blackbody has a particular spectral curve, as we can see here, and it's dependent upon only one thing: the temperature. And so how hot something glows and the shape of the spectrum is determined exclusively by the temperature. In fact, all these curves are exactly the same except for their temperature. They're just different scales. So if you could see them scale free, you'd see they actually have the same exact shape, but just different curves if we zoomed in. So if we zoomed in, we see that the 3600 looks like the 7200, except that it's shorter and farther to the red. And also the curve grows exponentially as you go. All stars are approximated well by a blackbody spectrum, meaning how their light is distributed across wavelengths. Okay. Now, a key thing about blackbody spectrum is it determines a thermal radiation. So thermal radiation is blackbody radiation, and we see that we talked about this before with Wien's law for blackbodies, and the maximum the emission peak for the wavelength depends only on the temperature. So whatever the wavelength is, the hotter it is, the bluer it is, meaning the shorter the wavelength is for the wavelength of the maximum, lambda max, which is the maximum wavelength, and the cooler it is, the redder it is, so that for the peak. So therefore, anything that's hot tends to look bluer, and anything cool tends to look redder. All right, so now if we zoom in and look out specifically at specific types of things, exactly how much energy is emitted per square unit area from a blackbody. And J is usually what we call the total energy radiated per unit area per second. So it's watts per unit area, or watts per square meter. And that's equal to sigma, which is that little O with a hat, sigma times temperature to the fourth power. All black bodies only depend, the total energy radiated only depends on the temperature of the fourth power. So if we know that stars are roughly black bodies in their emission, then we can utilize this to help us some more. So there is a relationship between the luminosity of the star and its temperature. And what is the luminosity of the star? The luminosity of the star is the total amount of energy coming off of the entire surface area of the star. So we can use the Stefan-Boltzmann law that says energy per second per unit area, and say what's the total surface area of a star, which is spherical. That's 4 pi r star squared, where r is the radius of the star, and you square it, and that little star asterisk at the bottom indicates that we're talking about a star. So subscripts always mean in equations what you're talking about, and superscripts always mean how many of them, or an exponent. That's what we see very, very frequently throughout all of physics and all of astronomy. So when you combine it, the total luminosity, meaning the total amount of energy emitted by the entire star per second, is dependent on the radius and the temperature. Now that 4 pi comes in because it's the surface area of a sphere, and the sigma is because it's the Stefan-Boltzmann law. So the luminosity of a star is proportional to the radius squared times the temperature to the fourth power. This is what's called the luminosity-temperature relation for all stars. If two stars have the same radius, then the hotter star must be more luminous. If two stars have the same temperature and one of them is larger than the other, then it's more luminous. Now, it's a really key question. Why didn't I use the word brighter? The reason I didn't use brighter is because brightness depends on distance. This is luminosity. So brightness is, well, it can be extraordinarily luminous, but if it's really far, it'll look faint, just like any star. All stars are intrinsically really luminous, but they're far, so they look dim. In fact, you can't see any of them during the day other than the sun. So this is the relationship between the total energy output of the star, its size, and its surface temperature. How can we get some of that? Because we don't measure the total energy coming off of a star. And it's really difficult, and we see in the sky that we can't really easily measure the radii of stars. So how do we actually get the radius of a star? Temperature. Well, let's see what we can do. On the back of a telescope, you can put filters. And so what we see here is, again, a telescope with a filter wheel on it with a series of filters. And what we're looking at now is a standard filter set called the Johnson-Cousins filters. And this has been around for a long time. And these are standard filters that many makers do make and create for use for astronomical purposes. And this is a Bader photometric R filter. We have these different kinds of filters. And these are commercial filters, and I just kind of nabbed it from a website. In any event, the transmission curve is what you see below. So the filters simply screw on and you send the light through that thing and into your detector, like a camera or something. That's all it is. All right. So what we do is we say that color, by definition, is the difference in magnitude. Magnitude is a measure of brightness, remember? And difference in magnitudes between two filters. So with the Johnson-Cousins filters that are in the visible wavelength region, meaning blue through red, we have three filters, the B, V, and R filter. And so all we do is we say, if something we can make 4 color measurements, and we can take the magnitude in the U and magnitude in B, minus the magnitude in V, and the magnitude in V minus the magnitude in R. We can make any two differences, but the most standard one that you'll see everywhere is the B minus the V. And that's because, well, the V is a general brightness, that R is kind of a tricky response, and B minus V tends to have the largest number of observations, and that stems from variable star observers that have been doing this for a long time. And so R tend to also not be as sensitive in photographic light, so there isn't a great historical record for it. But B and V, there is a great historical record. So there is by history and by dint of chance and by how things work that we tend to say in the standard way that one of the many colors that we can create will be the blue magnitude, the magnitude of a star when you pass its light through a blue filter or the B filter, subtracted from the magnitude of the star passed through the V filter. And that by definition is the color. So how do we get that out of there? So let's say that the difference in brightness between two colors gives us the temperature. How? Well, if we look at these spectra of stars, so we've got OB, AF, GKM type stars from blue to red on this diagram, we see an O type star is definitively brighter in the B than the V. And an M type star at the bottom in the red is definitively brighter in the V than the B. So remember, B magnitudes, the lower the number, the brighter. So if it's brighter in blue than in V, a very large negative number minus a small negative number will give you a large negative number. So the other way will be a small positive number minus a larger positive, meaning a large positive number minus a small positive number will give you a large positive number, which will make it more V. That's how colors go. So the more negative the color in the definition, the bluer. So we basically take the brightness between two filters in the standard filter set, and you can see that the different kinds of stars will have different brightness, different color numbers when you subtract the V from the B in its brightness. And this is just a standard way of doing things. So that gives you the color. All right, how can we work with this? So let's start with a series of stars. And specifically what we're looking at is the center of a star cluster. And this is the center of the globular cluster Omega Centauri as taken by the Hubble Space Telescope with 2 filters. And one filter is an extreme red filter, and the other filter is much more blue compared to it. And it just looks like a whole slog of stars out here. But our first task is we're going to separate them out. And first, we're going to separate them out by color. And so the bluest ones we will separate out on the left, and the reddest ones we will separate out on the right. We haven't changed their location in space, but we have separated them out so we see their separation in terms of blue and red. And so these are narrowband filters that specifically isolate them. And now we're going to then say, after we sort by color, which means their temperature, means the ones on the left-hand side of the screen are hotter than on the right-hand side of the screen. And then we keep going, and we separate now by brighter. Who's the brightest? We put the brightest ones at the top and the dimmest ones at the bottom. And look at that. We've got a really interesting diagram for this cluster. We've separated them out so that the brightest are on the top, the dimmest are on the bottom, the hottest on the left, and the coolest are on the right. And we get this amazing, amazing, amazing diagram. And it is this diagram, by simply taking the brightness in two filters and comparing it to the brightness in one filter, that gives you this amazing diagram. And so we have a whole bunch of things that we can label. We've got this thing called the main sequence, and we've got what's called the subgiant branch, and the red giants, and horizontal branch, and white dwarfs, and all sorts of interesting things. So once this was discovered in 1911 by Hertzsprung and Russell, independently they discovered it, it revolutionized the nature of physics. This had to be explained. It's not random. This is an enormous discovery, and the explanation for this changed the nature of astronomy and physics. So let's go look around. We could say each group has a separate set of names. Red dwarfs are very, very, very cool and dim stars, and those are red dwarfs. And if we then look at red giants, they're also very, very cool, but they're extraordinarily bright. So we got cool stars that are both dim, and we got cool stars that are bright. And RGB stands for red giant branch. And so then we can look way over here on the very hot stars that are very dim, and those are white dwarfs, or WDs on this diagram. And white dwarfs are hot but dim. And then we have a very interesting area where this line turns away, and where one line has a knee bend in it, and that's called the MSTO, or the main sequence turn off. Remember, we're talking specifically about a cluster of stars, and that is an interesting location, and that tells us a lot about the nature of stars. And then we have a different group here called the subgiant branch, or SGB, and there's something else happening in the subgiant branch. And these are interesting stars. They're called blue stragglers, which tend to be kind of outside that. And blue stragglers have their own interesting meanings as well, and they relate to binary stars. And then finally, we have the horizontal branch, which are very bright stars and very hot stars. And so there's something going on in each of these groups, and the explanation of the physics of them leads us to the understanding of how stars evolve with time. So, in the 1990s, the European Space Agency flew a spacecraft called the Hipparcos mission, and it made a catalog of millions of stars, and here are 22,000 stars from its catalog. The previous thing we looked at was from one star cluster. Now this is from a huge number of nearby stars. So it's got a lot of stars from here and a bunch of nearby stars, and we find that there's a very, very, very great large number of stars on this group that we'll call the main sequence. So between 80 and 90% of all the stars in the sky are found on the main sequence, and that's why it's called the main sequence of stars. And so that was originally called, and the name stuck. Remember, brighter goes up, hotter goes left, not to the right, but to the left. Luminosity is small at the bottom and big at the top, and you can also see that absolute magnitude ranges from about plus 15 for the dimmest and minus 10 for the brightest. And we can see the spectral class can be put across the top as well. But most importantly, there's our color definition right there at the bottom. And color ranges from the reddest are positive colors and the bluest are more negative colors. So that's what we've learned. The more negative the number, the hotter it is, the redder it is, the more positive it is in the difference between the Johnson cousins B minus V color. So we're relating directly the color to the luminosity or magnitude. So if we can get the absolute magnitude, remember absolute magnitude on the right-hand side, is we get the magnitude plus the distance. So if we can get the distance to a star and then we know its brightness, we can get its absolute magnitude. So if we get the distance from, say, parallax, we can get that. So this is amazing. So most importantly, we say that the luminosity can be derived from the absolute magnitude. And that's astonishing. All right, so now let's look at 85 to 90, between 80 and 90% of the stars, including the sun, lie on a diagonal band on the HR diagram called the main sequence. Now, on the main sequence, the luminosities of the stars range from about 1% that of the sun to about 1,000,000 times that of the sun. And the temperature range, though, is kind of narrow, from about 3,000 Kelvin up to about 60 or 70, 50, over 50,000 Kelvin. And the radii of stars along the main sequence ranges from about a tenth of the size of the sun to about 10 times the radius of the sun. And basically, the small ones are at the lower left, and the big ones are at the upper right. The coolest ones are at the lower right, and the hottest ones are in the upper left. And luminosity ranges dim, not so luminous, or dim at the lower right, and very luminous at the upper left. The next group is called the giants and supergiants. There are basically two main bands of stars in the HR diagram that are brighter than main sequence. They have the same temperatures as main sequence stars, but they're brighter. So they must be larger, and that's what the luminosity temperature relation says, that if for the same temperature, if one star is more luminous than the other, it must be bigger. And so remember, luminosity is measured because of the absolute magnitude. So you can have enormous stars. The radius of these things can be 10 to 100 times the radius of the sun, and the luminosity can be up from between 1,000 and to 100,000 times the luminosity of the sun. So giants and supergiants can be incredibly bright stars. And we're looking at supergiants, which populate the most distant upper reaches of the HR diagram. Their radii can exceed 1,000 times that of the sun, and their luminosities can be up to 1,000,000 times that of the sun. And now we go down to the bottom left of the HR diagram, we find that there's white dwarfs. Now, white dwarfs are hot, but they're also physically small. And this is a really weird area because these were kind of unexpected. They were seen to be stars that, therefore, since they have the same temperature, but they have almost no luminosity, they therefore must be incredibly small. So white dwarfs are about 1% of the radius of the sun. That's about the size of the Earth. So the groups of stars that make up white dwarfs are about the size of the Earth, and we know that because we can get their luminosities from their absolute magnitudes. Their absolute magnitude comes from their distance based on parallax or something else, and parallax will get you the distance, and then you take the color of the star and the parallactic distance and the brightness that you see it to be, and you have a group of stars called the white dwarfs, which are now known to be about the size of the Earth. That's really weird. That's kind of weird. And that's what we saw with Sirius in a previous lecture. Sirius B, a white dwarf orbiting the star Sirius. And it's about the size of the Earth. So now let's take a couple looks at some of the HR diagram notables. If we then take some prominent stars, some stars that you might know if you look out in the sky, such as Antares and Betelgeuse and Rigel and Vega and Alpha Centauri and the Sun and Sirius B and all those sorts of stars. They're scattered all over the place. And if you want to look where they are in the sky, take these names down and go look them up in the program called Stellarium. But we can see that they're pretty much scattered all over the place, but the stars that you know really well tend to be at the top. You don't know Sirius B very well. Barnard's star, we only know it because of this class. And Proxima Centauri, too dim to see. So pretty much the named stars are in the upper portion of the HR diagram. Interesting. So now if we just look at specifically the 100 brightest stars in the sky, all of them have an intrinsic luminosity much greater than the sun. Many of them have a radius much larger than the sun, and many of them lie in the red giants. There's a few blue giants, and many of them are in the upper left of the HR diagram, and they tend to be B and A and F type stars. And if they're G's and K's and M's, they tend to be giants. So many of the stars that you see in the sky are most of the rare stars. They're the brightest of the stars. We don't see most of the stars. You do not see them. So they appear bright in the sky because they're really luminous stars and they're not necessarily nearby. Let's see about the close ones. What about the closest stars? If we think about the closest stars to us within, say, 10 or 15, maybe 10 or 20 light years, and you can go to atlasoftheuniverse.com in order to see more of which one stars these are. You can get a list of them. we find that all of the stars that are close to the sun are cooler than the sun and main sequence stars, and there's a few white dwarfs. There's one or two stars that are hotter, such as Procyon and Sirius and Altair, but they are within about 20, everything in here is within about 20 to 30, 25 light years, and they're really cool stars. And most of them are much cooler than the sun, and there's a significant number of red dwarf type stars, which are way down in the M's. So a number of these, Epsilon Eridani is also another interesting one that's out in the sky. Alpha Centauri is the nearest star system, and Proxima Centauri is the nearest star, which we talked about, that has a planet around it. Sirius B and Procyon B are both white dwarfs, and Procyon and Sirius, hey, they're both nearby stars, and they both have white dwarfs as companion binaries, and Procyon B is a much trickier thing to catch in a telescope. But notice that the close stars are all dim stars. Interesting. That actually, let's go back for a second. What that means is that if stars are just kind of a random sample and we just happen to be it, it doesn't mean that only these kinds of stars live nearby us. It means that these are the most common types of stars, but they're also the least luminous kinds of stars, which means that they are the most common of all the stars. They're everywhere, these little tiny dim stars. They're all over the place. It's just the biggest, brightest ones that are the ones we pick out of the sky because they're really interesting and really cool. But the vast majority of all stars are less massive and dimmer than the sun. And that's what we learned in a previous lecture. And it's borne out because if you look at the 80 closest stars, you're taking a sample of an area of space that's kind of random around any given kind of star. And there they are, the dim stars. So we can further divide up, and let's say we can't actually get a very easy classification. Maybe it's hard to get a parallax on something, but we can always look at the spectrum. So there's a thing called luminosity classification. And if we look at the widths of the absorption lines in a star spectrum, then they can actually determine how big the star is. Okay, so if lines in a star's spectrum, those darker banded lines, become broader as the pressure increases. Why? The reason they become that the lines get broader is because under greater pressure, the atoms and molecules in the atmosphere of the star, or the atoms in the star, are moving faster. If they're under higher pressure, they're moving faster, which means if they're moving faster, there's a Doppler effect. If there's a Doppler effect, then it can absorb or emit wavelengths of light that are just off of their normal wavelengths, right? So an atom that's still, a hydrogen atom that is still, can only absorb light at 6,563 angstroms. And that also means that since it absorbs only at 6,563, that's when it's still. But if it's moving towards you, away from you, then it can Doppler shift that and absorb off of that. So the faster they're moving, the broader the lines when that happens. And that's because there's a higher pressure. Now, big stars are puffier, which means their atmosphere pressure is lower, so they're thinner lines. So therefore, large stars have narrow lines, and large stars are brighter for the same temperature. They have narrow absorption lines. And so therefore, big stars can be picked out. And so you can make a relationship, hopefully, between the narrowness of the absorption lines and their overall luminosity, and that's the goal. Well, we can have various luminosity classes, and the brightest supergiants, and this has obviously been done. And so you can look at the widths of lines, which is very subjective, but yet it seems to be easy enough to classify things into 6 different groups. And we have the bright supergiants that are the brightest of the giants, then the supergiants, bright giants, giants, subgiants, and main sequence or dwarf stars. So main sequence stars, like the sun, are called dwarfs. Everything else is a giant, unless it's a white dwarf, and white dwarfs don't have a stellar luminosity class. All right, so if we look at the various things, let's look specifically at K stars, and K stars span the range of main sequence all the way to the bright supergiants. And if we look at a supergiant bright K star, then the lines are extremely narrow. But if we then look at the main sequence version of a K1b, which would be a K star of the supergiant variety, not the bright supergiant variety, but the supergiant variety, we see that the lines are narrow because the star is puffy. Since it's puffy, the pressure is low. Since the pressure is low, there's very little movement of the atoms, so they can absorb only at their rest wavelength. However, in the main sequence star, the atoms are moving. And since they're moving, they can absorb light that's a little bit off of their normal wavelengths. And so therefore you get a broader absorption line. And if you can get the absorption features and stand them together, you find that one star compared to the other has exactly the same absorption lines, but yet one are broader than the other. If it's broader, it's main sequence, and if it's narrower, it's giant. So you can divide them up into various groups, and as you divide them up, you see that you can then relate the spectral type and the width of the lines to the luminosity, and that is distance independent because that's just the shape of the spectrum. So that's what we do with this. This is an amazing idea because this gives you a way to assign the relative luminosity of stars based on just their spectral line properties. So you can say, well, it's this luminous, and K-type supergiant stars all have this luminosity, and so you just calibrate the whole thing, and there you have it. You can just say, I found a K-type supergiant star. I know what its total luminosity is because I know its spectral type, and I know it's a K1b type supergiant star. And therefore, you can say, well, if that's its luminosity, how bright does it look to be? And that gives you a distance, which is really cool. There's a number of giants and supergiants can be distinguished between each other, and so we look specifically at K2 type stars. Epsilon Eridani is a nearby main sequence star, and it's a little bit smaller than the Sun. There's Arcturus, which is a prominent star in Bootes, the constellation Bootes, in the early winter sky, and we see that going up. And Arcturus is there, and it's a red giant. But Epsilon Pegasi, which is in the constellation Pegasus, is a red supergiant. And we can see that their radii are radically different, from a little bit smaller than the Sun to over 100 times the Sun. And then their luminosities range from 30% of the Sun to 4,000 times the Sun. But their surface temperatures vary quite little, almost none at all. And so just by looking at their luminosity class, we can determine their actual luminosities and therefore something about their radii. So the summary of all stellar properties there's a large range of stellar luminosities from 1/10,000th that of the Sun in the deepest, reddest dwarf stars to 1,000,000 times the luminosity of the Sun. There's a huge range of stellar radii from 1% the size of the Sun, or just like the size of the Earth, like the white dwarfs, to about 1,000 times that of the Sun, which are the supergiant type stars. But yet, given this huge range, there's not a huge range of temperatures between 3,000 and 50,000 Kelvin. And the mass range is also not that big. It's kind of wide, but for masses, but not as big as you might think. So it ranges from about 1/10 of a mass of the Sun to about 50 times the mass of the Sun. There are some much more massive stars, but they're exceedingly rare. And that all arises from this equation: the luminosity of a star is proportional to the radius of the star squared and the temperature of the star to the 4th power. And with this, we can plot the HR diagram, which is a plot of the luminosity and the effective temperature, find the effective temperature from spectral type or the color, make an estimate of luminosity from the apparent brightness and the distance, or even the luminosity class, and you plot that temperature from hottest to coolest and horizontal, and you get all these wonderful things. So again, the HR diagram was discovered independently, first made in 1911 by Hertzsprung, and Henry Norris Russell did a similar diagram in nearby stars in 1913. And so we use the form of Russell's as opposed to Hertzsprung, so Russell won the day in terms of the layout, but the stars don't land on just anywhere. They fall in those special regions that we've already discussed. So here's another view of the HR diagram, which is kind of a cool one. It highlights the Sun, which is a G25 type star. Betelgeuse, a winter star, is an M2 supergiant. Rigel is a B8 type bright supergiant. Sirius, one of the nearest bright stars, is an A-type main sequence star. Aldebaran, which is a K giant star in Taurus, the bull. But the most interesting thing is that why don't they have just any old luminosity or temperature? Why do they fall on this main sequence? Why are giants giants? Why are white dwarfs white dwarfs? Why are they this way? Why isn't it a scatter diagram? Why isn't it static all over the place? That's the big question. That's the central question for astrophysics. And in order to help answer that question, the Hipparcos satellite was launched in 1989, and it operated from 1989 to 93, and it made a catalog of over 1 million stars with high precision for their parallaxes to get their distances, and it took brightnesses and parallax distances, and also got parallax distances out to 2.5 million stars, and this was a major effort by the European Space Agency. And this is the HR diagram of 40,000 of the stars from the Hipparcos group. And again, they used the Johnson's filter system, B minus V, and compared it to the absolute magnitude, or just the magnitude of the star, absolute magnitude of the star in its visual band. So once you have the distance from parallax, you can get the absolute magnitude. And this is the HR diagram you get, or called a color magnitude diagram. But the most important thing that happened, it was released on September of 2016, was that the Gaia mission was launched and gave its first data set on September 14th. And it recently gave out its second data set earlier this year in 2018. And yes, it will change everything. There's over 1 billion stars now with parallaxes, and it has a slightly different filter system, but that filter system can be calibrated to other stars. But the 1 billion stars now give us an enormous understanding of the cosmos around us. And it was launched on 2013. It's orbiting well up past the Earth, the Lagrange 2 point in 2014, and it began in 2014 its science operations. It's going to get 1 billion stars over parallaxes for over 200 million stars, and it can get that parallax precision down to 10 micro arc seconds, which is astonishing. That means it can get distances out to 10,000 parsecs. So you really have to go take a look at this on the European Space Agency website, esa.int/Gaia, and that'll be and the first results came out in 2016. However, I just figured I'd go take a peek at their website, and we find that Gaia's HR diagram from their second data release, which they gave out earlier in 2018, was of 44 million stars within 5,000 light years of the sun. And they're plotted on here. And this is the HR diagram from all of those stars. And now we start to see subtle changes in the HR diagram. The giant branch has kind of a hook in it. There's a lump between the HR diagram of the bright stars, and there's a dearth of extraordinarily bright stars. There's also a huge number of dim stars that are on the lower right. And the reason it kind of tapers off so quickly on the lower right is because these stars are really dim, so it's very hard to find M-type stars and L-type stars and T-type stars because they're so dim that they're almost impossible to find by Gaia. But this data set, which shows some very interesting transitions of stars descending to become white dwarfs, and as well as the giant branch with this huge number of giant stars going off to the right, is a major, major, major change, and this will change the nature of many aspects of the study of astrophysics. So just for your amusement, here's some questions about the HR diagram. And you can look at this thing and have some fun and play some games with it. And let's say, if you look at stars D and E as indicated here, which one is bigger? If you look at stars F and G, which one is bigger? Which one would be bigger, star A or star G? Which one is hotter, star E or star A? Which one is smaller, star B or star C? Which one is smaller, star D or star C? You can play all sorts of games with this thing, so enjoy. And just for the last thing, back in 2011, I was at the Hudson River Museum and got them to, and convinced them to hang a whole bunch of little things from the ceiling, little lights and balls in it. And it was a really amazing diagram of the 100 stars within the closest stars in the galactic neighborhood. So we hung them from the ceiling, and unfortunately we couldn't get totally dark. It was sunny outside. That's what that paper is in the far wall. But there's me telling things about little stars close by, and I think I'm pointing to Alpha Centauri or something like that. And all the stars in the nearby neighborhood were posted, and we had nice tours and talking about what's in the local galactic neighborhood. And here it is, another colorful image of all the stars in our galactic neighborhood as held in by the Hudson River neighborhood. And all we have to think is that these stars, most of them are dwarf-type stars, and they're very, very dim. And even this diagram, this presentation that we did at the Hudson River Museum, was something that couldn't possibly be done in like total perspective, because these stars look big. And in fact, stars are incredibly far apart compared to their sizes. So here we were walking amongst the stars and seeing their positions in the sky, but not necessarily their real positions. All right, so here's some review questions. Go over them, have a great time with those, and stop the video to see what those review questions are. And I'll leave you again with this incredibly important diagram that tells us, and that diagram and the HR main sequence, the giant branch, the white dwarfs, and all of those things are incredibly important to tell us about the future of all stars, how they evolve with time, and why they do what they do. So now we're going to be going into the evolution of stars and their birth and their death and everything in between. All right, so that's what's coming up soon, and we'll see you next time.